Imagine walking along a beach that knows no sound of waves. The ground crunches like wet sand, but instead of salt, amber-colored organic particles slip between the grains. The air is so dense that breathing might seem easier, yet every movement feels slow, muffled, as if within an orange dream. Above your head, the sky is not blue but a veil of haze that softens the light until it turns day into a perpetual dusk. This is not an earthly desert at sunset, it is another world. Far enough from the sun for its energy to be reduced to a whisper, yet close enough for the physics of its atmosphere to remain surprisingly alive. This place joins the familiar with the alien with disarming naturalness. Here, rivers exist but flow with methane. Here, lakes have shores, contours, peninsulas, and straits, but are carved into ice as hard as rock. Here, it truly rains, but the drops are not made of water. Gravity is gentle, about 1/7 of Earth's. The temperature is a constant promise of frost, and time flows with seasons that last as long as the childhood of a civilization. Yet among grains of ice and carbon molecules, a coherent, stubborn nature takes shape, one that carves channels, piles dunes, and builds seas. This world has a paradoxical dimension. It is larger than Mercury, yet it is a moon. It brushes against the iconic ring system of its planet, and yet commands respect with its complete, self-contained personality. Beneath the orange shroud, processes stir that we would all recognize: evaporation, condensation, precipitation. Only the main actor is not water, but methane, joined by ethane and other hydrocarbons. If the surface conditions appear extreme, the atmosphere acts as a great mediator. It is thick, compressed by molecular nitrogen that makes up most of it. It retains just enough heat to smooth out the extremes and distribute available energy. But the same organic haze that gives it its amber tint filters light, subtracting photons and creating a unique thermal balance. A greenhouse effect that warms, and an anti-greenhouse effect that cools. The result is a frozen yet functional equilibrium, one that allows gaseous, liquid, and solid phases of hydrocarbons to coexist and sets low-temperature meteorological cycles in motion. Seen from afar, this atmosphere looks like a smooth film. But as you approach, banks of clouds appear, sometimes even convective storms that form during the warmer seasons of the sunlit hemisphere. Winters and summers here are not measured in months but in years. Winds can form global-scale currents that wrap around the moon, while near the surface, where methane's activity is most vivid, breezes sculpt familiar shapes. Thus arise dune fields stretching for hundreds of kilometers, aligned with the patience of ages, not quartz sand, but grains of water ice coated in organic crusts, aggregates of complex molecules created by ultraviolet light bombarding simpler gases. Those same photochemical reactions produce a surprising catalog of compounds. Among the final products are dark, sticky materials scientists call by an evocative name, as though they were leftovers from a cosmic kitchen that wastes nothing. If the atmosphere is the great theater, the surface is the stage where the actors leave their marks. Radar has revealed jagged coastlines and basins linked by straits and fjords. Some are as small as ponds, others earn the title of seas, hosting islands, channels, and deltas. Near the poles, especially in the north, these hydrocarbon mirrors form recognizable hydrographic architectures, their margins slowly shifting, perhaps due to seasonal variations in liquid levels or to chemical erosion of the icy substrate. Here and there, phantom spots appear and vanish in images. They could be rafts of organic material, gas bubbles, waves, or patterns of surface mixing. It is like watching an earthly shoreline at tide, except that here the tide deals with different viscosities and delicate gravity. In the midst of this theater, one day, an amber hemisphere welcomed a small probe from far away. Its descent through the atmosphere was slow, tens of kilometers of clouds and haze, its instruments open like windows onto a reactive world. The probe listened to the wind, photographed patches of terrain, sensed the texture of the ground, and landed softly on a dark, friable bed. There, the light resembled what we on Earth see a few minutes after sunset. The pressure was higher than at sea level. The cold, an enveloping 180 degrees Celsius that forgives nothing. In that brief hour of activity, the landscape appeared as a mosaic of icy pebbles, its granular skin telling of centuries of deposition and reshaping. Then came silence, but not oblivion. The measurements from that landing remain, to this day, a compass. Rivers, lakes, and seas are not mere scenic curiosities. They are clues to a methane cycle that must replenish the atmosphere. Otherwise, sunlight would destroy it in geologically short timescales. If the surface holds too little liquid to explain the abundance of the gas, then the source must lie elsewhere, or act episodically. Here bold but coherent hypotheses emerge. Underground reservoirs communicating with the crust, cryovolcanic phenomena releasing mixtures of water and ammonia along with hydrocarbons, or degassing processes tied to deep thermal cycles. Many regions display suspicious morphologies: domes, fractures, radar bright spots, isolated rises. No eruptions have been caught in action, yet the sum of these signs suggests internal activity. The alternative is that surface and atmospheric chemistry manage reserves and releases in subtler, cumulative ways. Meanwhile, tectonic dynamics leave measurable traces. Massive tidal forces, imposed by a giant planet, imperceptibly twist the crust. Fissures, uplifts, and depressions align along preferred directions, as if the moon breathes softly to its master's rhythm. Some high plains reflect radar more strongly and might represent the oldest terrains, surfaces that survived reworking. By contrast, dune fields and certain dark plains seem young, constantly reshaped by wind and precipitation. Even the few impact craters tell a story of erasure and rewriting. Their rarity does not imply a merciful sky, but a surface that renews itself quickly enough to mask its ancient scars. And as we scroll through the maps, an idea resurfaces that never ceases to fascinate. Beneath the icy crust, there may lie an ocean. Not a warm sea like our tropics, but a liquid volume kept pliable by the presence of ammonia, which lowers the freezing point and makes the depths more dynamic than the surface. If the crust varies in thickness, tens or hundreds of kilometers, down there the liquid might sway with the tides, brush against rock, dissolve it, enrich itself with salts, and store enough mechanical and thermal energy to generate convection. Such an environment, though dark and cold by our standards, is already a natural laboratory of long-term geochemistry. If such an internal ocean truly exists, the boundary between ice and rock becomes the world's chemical heart. There, silicate materials release ions and compounds, water dissolves and transports, and the energy of a body orbiting a giant drives cycles of lifting and compression. At that boundary, gradients of temperature and concentration could arise, those slow engines that, on Earth, sustain complex systems near hydrothermal vents. On such scales and under such pressures, even a reaction that seems sluggish to us might build new organized matter, layer by layer, over time spans unimaginable to humanity but commonplace for a moon. The surface, for its part, continues to offer scenarios where chemistry enjoys experimenting with alternatives. One of the most intriguing hypotheses suggests that, at such low temperatures, flexible membranes might form, not based on water, but on solvents like liquid methane. Some nitrile molecules, produced in the atmosphere and deposited on the ground, could self-assemble into vesicle-like structures, simple forms capable of defining an inside and an outside. It would not be life, as we understand it, but a conceptual step, creating compartments in which chemical reactions could concentrate, protect themselves, and accumulate complexity. At the same time, the abundance of heavier hydrocarbons, aromatic rings, and reactive compounds like hydrogen cyanide provides a pantry of prebiotic ingredients. If the word biology is still premature here, organized chemistry is a more cautious label, yet no less fascinating. And then there are the events that break the monotony of the Great Cold. A powerful impact, though rare, can locally melt the icy crust and create, for days or even years, pools of liquid water under high pressure, rich in salts and ammonia, temporary laboratories that, as they refreeze, trap intermediate products and traces of ongoing reactions. A young crater thus becomes a stratigraphic archive. Its layers record not only the impact but also the subsequent circulation of fluids, mineral precipitation, and exchange with the atmosphere. These are the very places where a future mission could search for chemical signatures of organized processes, or, more simply, measure how energy has been distributed through time. The constant action of the winds shapes the landscape like an obsessive sculptor. Linear dunes trace, through their orientation, the direction of prevailing near-surface flows. Their height and spacing speak of grain size, cohesion, and the humidity of methane in the air. When local storms develop, they can unleash sudden rains that carve channels and create miniature alluvial fans. As the liquids flow, they carry microfragments of organic matter, smooth icy pebbles, and deposit dark layers in topographic depressions. Where dark plains meet more reflective terrains, drainage patterns appear that resemble terrestrial river networks, though all adapted to the viscosities and surface tensions typical of hydrocarbons. In this intricate web, the shores of the polar seas move slowly, a thinning promontory, an island changing contour, a channel deepening, perhaps even oscillations in liquid levels due to atmospheric pressure or seasonal evaporation variations. The seas themselves hold unusual physical secrets. Unlike water, liquid methane has a density, viscosity, and surface tension that produce slow, gently rippled waves. The presence of ethane and dissolved nitrogen changes the dynamics, influencing foam formation and how effectively winds transfer energy to the surface. Radar reflections, moreover, respond to these parameters, allowing us to distinguish when a stretch is mirror smooth or ruffled by a polar breeze. Depth remains difficult to measure, but where signals permit, profiles reveal seafloors that are partly gently sloping, partly steep, perhaps carved into ice of varying composition. Where a temporary, phantom island, appears, some process, degassing, flotation of organic material, porous ice trapping nitrogen, shows that these seas are not stagnant ponds but dynamic, low-temperature surfaces. In the background, the question of methane's disappearance and reappearance continues to resonate. If photochemical processes destroy it, something must be replenishing the reservoir. Cryovolcanoes venting mixtures from underground. Networks of pores in the crust that, once saturated, release gas with changing seasons? Electrical discharges from charged particles locally heating surface layers and triggering degassing? Or a slow but steady transport from the depths, modulated by tides, connecting ocean, ice, and atmosphere? Each hypothesis leaves distinct footprints, collapsing terrains, domes, fracture mosaics, thermal anomalies, and the truth may well be a combination that varies over time and space. Within this puzzle, atmospheric chemistry tells another part of the story. Nitrogen, the undisputed king, hosts a multitude of guests: methane, ethane, acetylene, propane, simple and complex cyanides. When solar radiation and energetic particles break these molecules apart, the fragments recombine, forming ever longer chains, rings, and three-dimensional structures. Some of these products aggregate into aerosols that stick together like flakes, becoming condensation nuclei and slowly falling to the surface, feeding a dry, organic cycle that, over time, covers vast plains with a dark veil. Others remain suspended, altering the optical properties of the atmosphere, trapping heat at certain wavelengths and reflecting it at others, modulating the weather from dawn to dusk of each Titanian season. On the exploration front, the gaze grows more ambitious. If sending a lander straight down has already revealed so much, being able to fly would open up an entire geography. A rotorcraft powered by an energy source independent of sunlight could take off, glide, and land repeatedly, soaring over dunes, settling on dark plains, sampling and analyzing grains and pebbles, sniffing the air under different meteorological conditions. Moving at tens of kilometers per hour through an atmosphere friendly to flight, it would explore not just points, but contexts, sequences of sediments, transitions between terrains, potentially cryovolcanic deposits, edges of ancient craters that might preserve fleeting chemistries. A refined mass spectrometer on board would read the molecular inventory grain by grain. A seismometer would listen to the crust's tremors. Indirect hints of that secret ocean. Meteorological sensors would measure the breathing of the orange sky, distinguishing breeze from great seasonal currents. The journey of such an explorer would collect not only numbers, it would tell stories. Because each measurement, on such a world, is an outpost linking seemingly unrelated phenomena. A variation in composition within a dune field can explain the different radar roughness of a plane. The grain size curve of a deposit can reveal whether the transporting fluid was pure methane or a more viscous mixture. The presence or absence of nitrile compounds in a given area can tell us whether a recent rain has washed the surface or, conversely, if the air has laid down fresh material. Even the sound of wind recorded near the ground, its tone, intensity, and modulation, adds a piece to the local atmospheric dynamics, and when compared with dune shapes, completes interpretive triads that turn data into mechanisms. At that point, the questions about life become more mature. It is no longer about seeking organisms, but about recognizing organizations of matter that sustain stable cycles, selective interfaces, the ability to maintain gradients, and to use energy in non-trivial ways. Whether they are membranes in hydrocarbon solvents, functional polymers generated by slow but steady reactions, systems accumulating electric charges on aerosol grain surfaces, or transient chemistries in impact pools, each of these possibilities expands the concept of habitable environment, far beyond liquid water at Earth's pressure. And, paradoxically, by studying such a cold moon, we might better understand our own history. Nitrogen, cyanides, and simple hydrocarbons were key players on the primordial Earth. In a sense, that orange landscape is a mirror reflecting a frozen, reworked infant portrait of our own planet, Titan style. In the end, what makes this world irresistible is not merely the sum of its records, only moon with liquid seas on its surface, a dense atmosphere, surprising landscapes, but the way it forms a system, how it links sky and ground, chemistry and physics, the slow and the sudden, the micro and the macro. Everything moves with the calm of the cold, and yet nothing is static. An aerosol flake forming today will take years to touch the ground, but in the meantime it will have modulated the light warming a sea, and perhaps determined whether tomorrow in that region a breeze will rise or a cloud will thicken. A drop of methane falling on a dune is not merely a meteorological event. It is a decision about the mobility of grains, the shape of the crest, the direction of the next shift in the landscape. That is why returning there is not a technological whim but an intellectual necessity. Measuring sea depths more precisely, mapping fractures with accuracy, collecting samples in diverse contexts, listening to the whispers of the interior through the noise of the ground, tracking the breath of the seasons through an entire Titan year. Each of these actions narrows the field on the origins and fate of methane, on the existence of the ocean, on the ability of this cold chemistry to go beyond the mere sum of its parts. Meanwhile, even from afar, antennas will keep watch, awaiting the change of season, the birth of new clouds, the possible shift of the seas from north to south as models predict. Each new snapshot, each spectral curve, each radar reflection refined will only make the portrait sharper. When the story is more complete, we may discover that its resemblance to Earth is not an aesthetic coincidence but a clue. The processes that produce order 1.5 billion kilometers away are merely variations on a universal theme. Wherever there is an atmosphere that transports, a surface that collects, a depth that pulses, and an energy that, however small, never disappears, there, matter tends to organize. That is the promise hovering above the dark dunes and amber seas. That within the great cold may lie another kind of warmth, the warmth of things slowly learning to become a world. And so, the true reason we raise radio telescopes, launch probes, build drones for alien skies is simple. To listen to how, elsewhere, the cosmos tells its own story of wanting to become complex. Titan is a clear voice in that choir, and it is worth following it until its music has taught us all it can, about itself, about us, about the art of nature in writing stories through chemistry, gravity, and time. If you've come this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.